hide. Okay, so this presentation is a work in progress. It's entitled "What is Charge? What is Mass?" Because these are the two basic concepts that I've been struggling with since I was a student. And when you taught physics or engineering, you go to the first class and they say, well, mass is the ratio of or the multiplication of density and volume as Newton defined it, or some other definition, depending on the domain of physics. And it's over within 5 seconds, and you're on with the more sophisticated theories and everything. And the basics never. If you ask about the basics, they say, well, learn a bit of physics first, and then you get some knowledge about the basics. And of course, you go on through your whole career in university, and you don't really learn about the basics. And this is an attempt. It's a totally inadequate attempt, but it's an attempt nevertheless to try and get to what is behind these two things: charge and mass. They seem to occur together, and but one is the force of charge. The force between two charges is vastly in excess of the force between two masses in gravitational mass terms. So we'll that's it. Right. So I'm just because I've got loads of slides, and so basically my philosophical approach is the unity of nature. So you shouldn't have all these, like the domain of gravitation, the domain of electrical, the domain of quantum field theory, etc. You should all just have one theory, and all the concepts should be consistent over the whole of the subject. Well, that case is not true now. I believe in realism, although not everything can be measured. I mean, basically, you either have to rely on concepts of ether, which you can't measure directly, or you have to have some other underlying concept to bind everything together. So we always end up with non-observables, and that's not to be afraid of, because mainstream physics has unobservables all over the place. And the basic idea is just trying to minimize it and minimize the number of observables and make them basically the structure of the whole thing should justify the unobservable or the assumptions you make about unobservables. And belief and skepticism, well, it's easy to fall in love with your theories or the first ideas, and I always try to balance between belief and skepticism. So you need belief to try and work on something. Basically, you're taking a bet on a certain idea, and you have to put a certain amount of work in. But at the same time, you need to be skeptical about it, because it might not pay off, and when to give up. I mean, the in mainstream physics, they've spent 50 years on string theory research, and it seems to be not paid off at all. And there wasn't enough skepticism in the process to try and avoid that 50 years of effort to go effectively nowhere in terms of what they originally wanted to achieve. I.e., unified theory of physics. I mean, analogies are all over the place in physics, and you don't have fluid analogies for electrical things. They have Newton's law that people often use the Poisson's equation, the electrical or fluid equation, to try and understand gravity. We have analogies jumping all over the place, and that's part of the deal. But analogies don't actually prove that something's correct, and like the electrical analogy for gravitation, you end up with a positive and negative mass effectively as a variable, and negative mass doesn't exist, or has never been observed, and would lead to absurdities in physics if it did exist. So mathematical considerations, well, that's my pet thing. Applied mathematics has no clear foundations, because pure mathematics, they say that infinite things, infinite sets are part of the foundations, but that has no place in applied physics, applied mathematics used in physics. And a measurement theory, dimensional analysis, I've talked about that in the last talk I gave. And engineering and science, as people have been talking in this channel before, is more than just mathematics. You've got to balance the qualitative with the quantitative, because you can't rely on one or the other and hope to get make serious progress. Only one or the other. You have to sort of balance between the two. Right, I'll just skip that. There's certain things you should be aware that all these constants and used in current physics are all interrelated, especially the classical ones, and mass appears as a dimension, and if you have mass on one side of the equation and have mass on the other, you can't ever understand what mass is, and that's the nature of dimensional analysis. The two things should match up. So you've got to have mass and, say, ether, or mass and something else, and try and connect the two. So you almost have to break the laws of dimensional analysis to make progress in understanding things. But the same thing goes for charge Q here, that if you multiply the permeability of space and the permittivity of space, you get the speed of light squared, so 1 over, because the Q's disappear, the charges disappear. And you can't, maybe the charge has got length and time, ways of measuring it in terms of length and time that would make sense, but we don't know. So the dimensional analysis really doesn't give you a guide on how to make progress. It only sort of gives you an indication of your that your physics is consistent within a certain agreed framework. I hope that makes sense. So the Ritzian isotropically compressed ether is basically a base biscalar ether, and it's basically an analogy of a hydrostatic analogy, in compressing things by the same way in all directions. So in 3 directions you compress isotropically, or alternatively a tension, and that in that way you can, because in elastic solid elastic ether theory, you end up with tensors quite easily if you have different forces or stresses in different directions. So you can simplify the whole thing by just making everything hydrostatic or isotropically compressed ether. And that's basically something that can be followed up if you look at the way that Ritz criticized Maxwell's equations in his Researches Critiques Electrodynamique Generale. And that was picked up by Alfred Rayleigh, and I've given the Rayleigh, and I've given the basically quotation of the page 60 to 65. He basically discusses the localization of energy. I mean, that formula that I'm giving on the page, where E squared plus H squared, is basically the localization of energy in Maxwell's theory, but it's not unique. You can have various ways that E and H can be distributed in the field, and I sort of want to look for a unique way of doing it, or one way of doing it, one preferred way of doing it, and Maxwell's theory doesn't give you that, and so it's in fact the opposite. I mean, people make a big thing about the fact that Maxwell's theory in terms of scalar and vector potentials, which is another way of writing Maxwell's equation, can be put in infinite number of ways. It's basically called the gauge basically gauge symmetry, and I mean, and that leads into particle physics, but I don't want to go there, because the basic point is that it's not unique. If you want to create an ether theory to back up or to derive Maxwell's equations from it, you've got to find a way of uniquely defining the ether. And the simplest way to do that is in terms of a scalar or biscalar. And if you just have one scalar, you can't do anything with it. You can only calculate the derivative, 3D derivative at any particular location, and that doesn't give you enough information to derive, or potential information to derive, both gravity and electrical forces from the one ether. And that's why investigating the next simplest, which is a biscalar ether, where you have two different scalar properties which you can take the derivative or take the integral of, is the next more complicated thing. So that's the basic idea here, is to take the simplest idea and see if you can get make it a toy model and try and see if you can make progress. Hopefully this will make sense, but I've gone too far. There's a slide. There we are. Sorry, I'm just struggling with my... Right. Problems understanding Newton's gravitation. Now, it seems simple enough, but Newton... I mean, this is in the modern mathematical form. Newton didn't have a constant of gravitation, but that was basically measured by Cavendish using the Cavendish experiment. So now we have an experimentally determined G. M1 and M2 are two masses that that gravitationally attract each other, and they're linked with the forces. So we have various questions. This theory occurs in physical space. We don't know what physical space is. In fact, every different theory has a different idea of what physical space is. Well, that's the most understandable thing. It's just a straight line length between two masses. But how do you define straight line? As obviously that's been questioned by the non-Euclidean geometry and Einstein's theory of general relativity. So, what is force? I mean, it's Newton's second law. But should we have force? Is it the right way to go? Because Einstein trying to eliminate force, but yet all engineering depends on force. You need force to make measurements in terms of experimentation. In any experiment requires an actuator or some piece of measurement equipment, which will often rely on forces. So so what is A? It's acceleration. How do you define acceleration? Is it relative? Is it absolute? See, the mass is one inertial, one gravity. No, they're not both inertial masses, because there's only one real definition of a mass in terms of measurement, and that is inertial mass. So the G includes a mass in its dimensional definition, which is an inertial mass. So it effectively defines gravitational mass and inertial mass, or the ratio of the two, as one, which is what Einstein assumed in the strong equivalence principle. But it's basically assumed in the whole physics from before Einstein made that as a principle or as a assumption. What is the speed of F? That's never really been answered in Newton's theory adequately, because the speed of the interaction doesn't seem to occur. It's almost independent of the speed of interaction, because if you assume that, like with other fields, the speed is c, or the speed of propagation is c, then where is c in this? It's not clear how it pertains to Newton's theory. Right. So to answer the question over acceleration, this is how this is how I was taught in engineering physics, Newton's law. You basically have an absolute space, and individually each mass accelerates towards the other. So A2 accelerates towards M1 based on that mass M1, and vice versa. And when you multiply through by the mass, so M2 multiplied to A2, and it multiplies on the other side, you get and the same thing on the other side. You get basically the same equation on both sides. But it's basically because there isn't a relative acceleration. Well, there is, because it's the relative acceleration is A2 plus A1. And normally you're considering, say, a mass that's attracted to the Earth as being so small that it doesn't accelerate the Earth by any measurable amount towards it. So you can almost ignore that one. So that's why we say all masses are accelerate towards the Earth by by exactly the same g acceleration. But if you have a significant mass compared to the size of the Earth, it would obviously be measurable, and those occur. I mean, Newton said it was in terms of absolute space, but it's almost like it acts as a solid body, and everything, as long as you calculate everything via the center of mass, you consider it as a solid body that's moving, orbiting another thing like a galaxy, or the galaxy orbiting a cluster of galaxies. So as long as you account for everything around the center of mass, that is the one point that doesn't change. In a two-body system, in a three-body system, I don't know whether mathematical proof is, but it's basically seems to be true that any number of particles, the center of mass of the system doesn't move, so that can be considered the stationary point. And of course, that won't be the absolute a position in absolute space, because that itself can move with a constant velocity, or even acceleration around another body. So it's basically all the internal forces can be considered to move around a stationary barycenter. It's basically so. The reason I'm saying that relative acceleration is A1, A2. That's part of my deriving the Newton's law later on. Let's move on. Right, I think I've been over most of this. So these are the basic dimensions of everything. Right. Oh. Just. Right. So in the time of Newton, the concept of energy wasn't well understood, as certainly as well understood as it is today. Leibniz gave the first ideas, but it integrates perfectly well into Newton's theory, and there was discovery of new planets, and originally they thought, well, in fact, Newton thought that his theory wasn't perfect, and that he even had the idea that God meddled occasionally to keep the whole thing stable. But Laplace, I think it was, did some very detailed analysis and proved that what was assumed to be secular orbits, i.e. things that change without coming back, without going into sinusoidal oscillation or coming back to the mean, he proved that these long secular orbital changes actually do come back on themselves, and it's a stable system. So so it was a basically fantastic innovation, Newton's law. I mean, it's just amazing, so simple. Right, so but it was proved wrong. So I just there's the anomalous perihelion shift of Mercury. You can't use the Newton's law to find a planet, because there doesn't appear to be a planet between Mercury and it was called Vulcan, but between Mercury and the Sun. Electromagnetism does not reduce to Newtonian mechanics or vice versa. And which is the more fundamental theory? Because quite often people choose Newton and try and prove electromagnetism or vice versa. And deflection of light from the sun, that's sort of included in Newton theory, but it gets the value wrong. It's half the value of Einstein's theory. But that should really be an electromagnetic theory. And if you're showing the gravitational theory, it's sort of two domains that overlap but inconsistent with each other. GPS, gravitational effects on length and time, which have been discussed numerous times in this group. Deflection of light by galaxies and dark matter. Well, I don't necessarily believe in dark matter, but if it's there, it deflects light. Laser ranging of time of flight, that's another electromagnetic effect. Gravitational waves, it's debatable whether that's electromagnetic, but it should be part of a single theory. And the question of, we haven't solved dark matter or modified Newtonian dynamics, and I'm in the modified Newtonian dynamics. I made my bet on that one, but that's undecided at the moment. And there are cosmological difficulties, with Newton's theory. I mean, especially in terms of an infinite universe. There's if it's infinite and you haven't got an upper limit speed, you can't actually calculate the gravity anywhere, because because the effect of all the other infinite parts of the universe will override any local forces you have. So it's fine if there's a limit to the size of the universe, or there's an upper speed, which we believe that the maximum speed of propagation of gravity is c now, and that limits the extent to which basically creates a visible universe boundary, and you can't see parts of the universe older than it takes light to travel for the length of the universe to reach. So there's a sort of limit, even if the universe is bigger than our visible what's visible to us. In fact, as the universe ages, the more and more comes visible to us under the current ideas. So the universe does seem to get heavier in total, the total mass of the universe we see. I'll leave this. It's just basically the legacy of all these unanswered questions. I mean, is light bent rather than refracted? I mean, because if in an ether theory, ether provides the medium to refract light, and obviously you've got to get the magnitude right. The Newton's theory, it was half what it should be. So there seems to be a refraction element and a rescaling of what we mean by length in gravitational fields, and that's how Einstein achieves the doubling. Of course, if you look at special relativity on its own, you can get half the effect as well. So I don't know. It's all confusing. If you don't have one theory, you can basically explain things multiple ways. It's very difficult to understand. Poincaré's conventionalism, he basically said at the end of the day, if you create a Euclidean theory with the ether, say, or a non-Euclidean theory with curved space-time, as in Einstein, you should be able to marry them up, assuming that both theories are ultimately correct. you should be able to have some conversion between what you understand as a force in Euclidean theory and what you understand as the equivalent in non-Euclidean or general relativity. And one example is the Pythagoras theorem in Euclidean theory, as I've given, and in non-Euclidean it's altered. And so I don't worry too much about what theory, because ultimately at the end of the day, when everyone gets these theories right, you should be able to convert between one view and another. I mean, that's the ultimate aim. I mean, people are critical of Poincaré's view because they don't really understand it. But anyway. Then there's the difficulty of action at distance or action by contact. I mean, this is the fundamental problem of understanding physics. Even though pure Newtonian theory is action at distance, Newton didn't believe in action at distance, but he never really. I mean, he made a few queries in his optics, his book on optics, that basically guided people towards an ether theory and of varying density. The ether could vary of different density depending on how far you are from a material body. But it was never really a mathematical theory. It was a qualitative argument. And around the time of Faraday, the continental Europe embraced action at distance, and Faraday obviously developed the field theory that was taken up by Maxwell and other British physicists like James Clerk Maxwell and Lord Kelvin. Also the Irish Fitzgerald, Heaviside, basically all the people who got involved with developing Maxwell's theory thought of only in terms of the concept of field, i.e. there wasn't action at distance. They want to get rid of action at distance. But the need for action at distance has actually been revived because of the way quantum mechanics and the QED has been developed, because it isn't properly a field theory. It's related to the fact that you can't have this basically a unique, basically a unique ether, unique frame of reference. I mean, I don't understand exactly all the details of that, but the intellectual battle is one that's been going on for the 300 years, and it underpins basically everything. When you get down to it, it's all down to this difference between action at distance and action by contact. Mathematical space, we'll leave that. So what is physical space? It's still an unsolved problem, and I've talked about Newton's view in optics, and Newton had a sort of scalar space. In fact, until vectors were developed, people thought qualitatively in terms of scalars. In fact, Faraday was basically an archetype of that. He didn't really think in mathematical vector form. There were others as well. I mean, people that have influenced me. Basically, qualitative ideas are basically dependent on thinking about scalars, because that's the easiest way to think. But how do you marry that up with the real world where vectors are everywhere? Velocity is a vector, electric fields are vector, all these things are vectors. Yet underlying the whole of the thing maybe there's a scalar thing that is basically a level down below Maxwell's theory, and then that justifies it. Maxwell used quaternions. That involves a scalar and vector space combined, a single scalar and then a vector space combined, and Heaviside basically was involved in getting rid of that. He simplified everything to vector space only in Maxwell's theory. I think, how do we define a straight line? I mean, it's quite difficult. A straight line is involved in inertial frames. If you have a body, the Newton's first law, basically, a body in an unaccelerated motion, it will carry on forever in a straight line. But obviously, that's disturbed by gravitational fields. So you sort of get a straight line orbit at a sort of infinite distance for any gravitational body, but we don't really define a straight line as as the curvature at infinite distance from a circular orbit. But you could do, I suppose. It's something to think about. This was just to remind me to do that. One major feature of Newton's theory is the gravitational shell idea. When you calculate the gravitational attraction of a body inside a gravitational spherical shell, it doesn't have any effect on the body, gravitational effect on the body. So there's no net force. So it can be anywhere in the shell, and that's because of the 1 over r squared effect. And but it somehow, I'll come in to talk about Mach's principle later, but in Mach's principle, he sort of said the only way to get away from the absolute space and Newton's idea of the bucket and everything was to believe that these shells exterior to us, all these all the mass in the universe in the shells that are increasingly distant from us somehow do have an effect, because he said it was not necessarily sensible to define a absolute space which we couldn't really properly define, although we can define it in terms of the stationary frame of the cosmic microwave background radiation. Now, at that time there wasn't a way to define absolute space, and Mach believed you should be able to define what you're talking about. So it's almost like the main feature, or one of these main features of the gravitational shell, and then nothing works and nothing is attracted inside, is something we've got to think about and maybe adjust. I've talked about his acceleration absolute relative. So what is mass? Because there's inertial mass, which is the F equal ma, and there's gravitational mass, which is basically a static formulation. So there's if you've got two masses and they're and they're strung up by little cords, very thin, low mass cords. There's acceleration due to gravity is a sort of static effect, and then that static effect leads on to a mass being accelerated, and then the mass accelerated due to its inertia. So there's two elements to Newton's law of gravitation: a static effect and a dynamic effect. And the static effect is a gravitational mass, and the dynamic effect is inertial mass. But there's no way of differentiating in current theory. In fact, Einstein believes they're in the strong equivalence or something equivalent. So the ratio of inertial and gravitational mass should be unity, i.e. exactly the same. I've repeated myself there on the straight line motion. I'll just... Newton's third law is really critical. It's probably the only law that is really exact, and yet in Einstein's theory, we tend to have one body approximations, and it's sort of unsatisfying to remove the third law from our gravitational theory. So G, as I said, is experimentally determined. There's no agreed theoretical value for it, and I believe that it should be a way of calculating G based on other cosmological parameters. I mean, Dickey was famous for using Mach's principle to try and calculate G. And if you look on the videos of Alexander Unzicker on the YouTube, you'll see plenty of videos where he discusses this. What is the speed of F? I don't know. It seems like, as I say, the Newton's law almost eliminates it as a parameter in the solution to the problem, and I'll come up with the ideas of why that should be in a bit. Everything in classical physics is a force-energy approach, and I'm trying to argue that there's something below energy force, below Maxwell's equations, and that would be a scalar ether. I mean, a few other people, John Hodges, come up with a scalar theory of anything. Mine is a slightly different scalar model, with a biscalar model. So one of the greatest physicists in the last 40 years is Milgram, because he's come up with this Mond phenomenology. I can't pronounce it. And it's basically tied together huge amounts of observations, cosmological observations, and it's a way of maybe not getting rid of dark matter entirely, but certainly reducing the need for it. And it's all based on the idea that Newtonian gravitation is modified at small gravitational accelerations, of the order of 1.2 times 10 to the minus 10 and below, and that's of the order of c squared over r, or c squared over 2r. That's that sort of scale. Right, now we get on to trying to derive Newton's law, and this is basically the Ritzian Aether idea. It's basically a compressible ether. S is an analogy with pressure, but pressure normally contains the unit's mass in terms of But if you strip out the unit's mass from pressure, you have a something called acceleration per unit's area. And I mean, you could put the ether in that, but we can't measure the ether. If you put the ether in, you'd have the units of one. So I'm leaving ether out and just saying, well, there's something below mass that can be measured in acceleration per square meter, and that's S. That's a pressure. That's the pressure of the universal physical space, and there's a compressibility that's associated with it, and the formula is beta S squared. It's very simple. It's a linearized. I'll just show you roughly how I get that. If you do elastic tension in one direction, elongation, you get the elongation. There's a thing called Poisson's ratio. So when you elongate something or compress something, the elongate it, the actual dimensions and the perpendicular directions reduce. So you have to calculate all that, and you can calculate the work done. I'm not going to go into huge detail on this. People can ask questions. And then when you calculate the strains in all directions, if you assume they're the same, you get this middle formula. Du equals the pressure divided by Young's modulus, and the Poisson's ratio is included. And for linear approximations, you can relate Young's modulus, bulk modulus, and Poisson's ratio by this formula. And then this allows you to simplify if you use the bulk modulus or compressibility. So there's a route to this. So you don't have to use tensors. I mean, if you assume there's different tensions in different directions, you have to use tensors because there's but you can simplify it. I don't know why this hasn't been used. I haven't seen this developed anywhere. Now the basic idea is that that there are points which the compressibility is altered by 1 over r, and the compressibility is one basically big homogeneous variable, and it's altered by the two masses, by 1 over r1 and 1 over r2, and we can calculate using geometry what they are. And so we get the bottom formula. And we integrate over the whole of space, so to the volume or radius of the universe. And we get to this formula for U equals this sort of constant bit, which involves Ru, the pressure of the universal medium, the background compressibility, and these K1 over D and K2 over D. And if we differentiate it, we get an acceleration and a constant. The half over beta zero disappears because in the differentiation. And if we swap K1 with some sort of mass term, depending on K, with a constant K, we get an acceleration which is equal to this term here, and we can replace that term involving K with a gravitational constant. And then the relative acceleration is this, which is the sum of the absolute accelerations, where A1 and A2, or not necessarily absolute, but accelerations relative to the barycenter. And then you basically get to Newton's law. But with a constant that involves a k. And for years and years, I mean, I started thinking about this in 2013, well, probably before that. And this k has always stymied me. Probably because I won't talk about inertia because that's another issue. So I'm going to try and get to k via Dirac's large number and max hypothesis. And this is a strange way to argue, but anyway. So Dirac's large numbers comes from this idea that we want to calculate the force of between two charges using Coulomb's law, and the force of two masses using gravitational law. We want to compare those two. And obviously, the force in the Coulomb's law is vastly in excess of the sort of order magnitudes of forces in Newton's gravitational law. And when you calculate it, it works out about some value times 10 to the 39. And that's one of Dirac's large numbers. Now, this is a well-known formula from the Friedman cosmological model, and it basically is the critical density, basically the density that defines whether the universe is closed or open. So if you have a density above this, then the universe should collapse in on itself via the force of gravity. And so we rearrange that formula as Andreas Sies did in his book Relational Mechanics, and we put in a fudge factor, which is xi. Xi has a value between 4, and 4 is the critical value, and it probably between 4 and 10, so it's got a relatively small range. And if we substitute for the Hubble constant, so the Hubble constant is C over R, which is the definition. Basically, it defines the radius of the currently observable universe, and we get a formula for G, which involves C squared over the density of the universe, average density of the universe, divided by R squared, which is the radius of the visible universe. And we try and simplify that, putting in the classical concepts of density and mass, and then we get to this. Get to this formula 2c squared R over m with the fudge factor, which is basically defines the value of G, and this is basically argued from Mach's principle in Sies's book in a sort of very heuristic way. And if you get a value of xi about to 7.9, you get the accurately you fit the value of G basically. So the current theory, standard model of cosmology, is that the universe is close to the critical matter, closure density, and that this is not possible with just ordinary matter. So that makes up 16% apparently, and 84% is invisible non-baric dark matter. So if you just include the dark matter term, there's the Xi fudge factor is 5 on its own, and for ordinary matter it's 25 on its own. Now, This is a classical link between the radius of the electron and its charge, and so the basic idea is that the smaller the radius, the greater the energy of the elementary particle, the greater the mass. So if we normally it's put me equals something over re, and we rearrange that so we get a value for the classical radius. So we take the formulas for G and Re and then substitute them into the comparison between the two forces we got earlier. And we get this formula, which is Fe over Fg. Whoops. Oh, it's gone on previous. We get Fe over Fg equals Re, the electron radius, over the radius of the universe, multiplied by the mass of the universe over the mass of the proton. And I said earlier that the radius of the visible universe is growing, the mass of the visible universe is growing, so the overall ratio is growing of Fe. So this can't be a static formula, and people don't like thinking about this sort of thing because it sort of doesn't square with our current ideas about how the universe evolves. And Dirac himself thought that G changed with time, but the other possibility is C changed with time, or they both change with time. But something has to change with time, either C or G, the gravitational constant. So Re over Ru is roughly another 1 over a large Dirac large number, and the mu over mp is a square of a large number, and they're basically all linked in the same formula. So the three numbers aren't independent. So where do the large numbers come from? I mean, this is the question that's not been answered ever. So I've got this thing where so that these things change, that they all change. So this is, I've basically already said this. So this brings me to how I leverage or heuristically leverage some sort of idea about what the ratio is between mi, which is the inertial mass, and mg, which is the gravitational mass. And according to the strong principle of equivalence, of course, they're the same, and the ratio is 1. According to the weak principle, there's a value k, but the k can be absorbed in g, so it's difficult to argue whether there's much difference between the theoretically between the strong and weak. I mean, there is a difference, but it's very hard to fathom how to understand that difference. So what I want to investigate is the non-equivalence of gravitational mass or gravitational a measure of gravitation, and so the non-equivalence is that they're actually completely different units of the two, which is an outlandish thing to say, but I'll just follow with the logic. The gravitational mass and inertial mass are assumed to have different units, and therefore the value k is a dimension number. So we just go through. So we get this thing called n eta. The Greek letter eta is what I've used to describe the gravitational mass. So the constant is the one associated with it. So that has different measurement units to normal mass, eta g. So this was the first part of what we derived earlier, g eta. So we've taken out the k part and explicitly put it separately. So the RU is self-explanatory, and S, as I said, is an acceleration per unit area. So basically, S is in our measure the rate at which the universe is expanding, the accelerated expansion of the universe, AU, and the RU is the surface area at the radius of the outer limits of the visible universe. So we can calculate S squared as well. So we can simplify. I'm just getting different terms in terms of G and K. So it depends on A squared, AU squared over R, 12 pi. Now to fit in dimensionally with the value of K, we have to put in something like 1 over density, average density of the universe times the rate at which the universe is expanding currently, the accelerated expansion, and you put the numbers in, and you get another direct large number, but this time a dimensioned direct large number. Oops, sorry. So if I put in the values for K, we ultimately get this value for G of the accelerated expansion of the universe, the times the radius of the universe squared over mu and a factor of 9. But AU is unobservable in the sense that this model is a sort of pressure bubble, and so the bubble has been expanding outwards, but at a certain acceleration. But the matter inside the universe is under gravitational attraction towards the center. So there's a slight correction. So the observed acceleration, what we observe, is AU minus AG. So what I've calculated as 9 GM minus thing. So the actual acceleration we observe is slightly less. And equating Assis's theory with my ideas, you can sort of justify that AU in this model is 2 c squared over R, which is about 4 times 10 to the minus 10 in acceleration terms. And we've got eta a value 9 compared with the value 7.9 we calculated earlier. I mean, this is just a toy model demonstration. It's not. I'm not saying this should be thought of as canon. But what I just want to get to the point where what we understand about charge should be linked with the universe as a whole, and there's a coincidence between the acceleration that I've calculated, which might be spurious, and the value of E, because the value of the elementary electronic charge, it seems to be about the square of the of this accelerated, and this is probably a bit high, but in sort of rough terms, is about the square of the rate at which the universe is accelerating in its expansion, which is coincidence, or I mean, in the way my mind works in terms of constructing physics, I want to create this link, and whether this is the link or just a complete mistaken idea, it doesn't matter. This is the direction I want to go in. And now we come into Coulomb's law. Coulomb's law is completely different to gravitational law. It's the charges can be plus or minus. Well, it's the same form, but the charges can be all plus or minus, as shown here. So the force can be either attractive, as in Newton's law, or repulsive. And if you try and analyze from my point of view, and you assume that accelerations are these accelerations are scalar in the sense that the acceleration is outward in all directions. So although that accelerations are vectors in isolation in one direction, if you have a hydrostatic arrangement and accelerations in every direction, it's a sort of pseudo scalar, I suppose. So I've taken that liberty. But if you want to create Coulomb's law from accelerations, the mass doesn't behave in the same way as Newton's law. You end up with this when you create the relative acceleration, which I assume I want to get to via my theory, by my extension of my theory, which I haven't achieved yet. You end up with this 1 over m1 plus 1, which is basically what you end up within the early forms of quantum mechanics to allow for the center of mass in the calculations. So it sort of gets, even if there isn't, this toy model is funny. It's almost directing in the right way, but it's I for life of me, I don't understand it at the moment. But anyway, let's move on. I've run out of time, I think. I've gone over time, so we'll just. I was going to talk about Poisson's equation and the fact that it's based on a analogy with fluid flow. In fact, Riemann, who wrote a book on electromagnetics, believed that at a positive charge and a negative charge were sort of infinite points where all the flow disappeared into another dimension on one side and reappeared on the other. So, and my argument is basically that that's the wrong approach to try and understand gravity. The weak force in my model, when you put together the model of the charge, which is basically S is the overall pressure of the universe, my idea is that when you create a charge, you create. I mean, it's sort of like Dirac's idea, but slightly different. You create a hole, so you end up with a ds, which is the delta charge, which is exactly the same as the overall universe pressure, and the hole obviously is the negative of that, and they both have properties which are symmetric, even though they're completely different signs. Now, in the weak force, the idea is that the more massive you have, the more compressibility of the ether is changed in locality around the mass. So in the weak force, you assume there is one massive particle, say the nucleus, and another particle, say the electron, and it's asymmetric from that point of view. And the compressibility is not just the cause of gravity, but it's actually weakening the electric force, or the effect of the pressure in the model. And the strong force is just a symmetric version of that. So the nucleus held together not by a strong force, but by a weakening of the electromagnetic force. That's the direction. And even though it's a toy model, there can only be four forces, because there's, in binary terms, there's two variables: the compressibility and the pressure. And you've got two things which you can have two values. So it's a four. Or right, finished. That's hopefully something of my ideas in my brain have been dumped today. So I don't know how people are going to respond. But hello, can I?
Well, thank you very much. Yes, I must confess, I was just about to come in and say there's a lot of very interesting material here, and rather than curtail the proceedings, we might ask you back to give a second part to it. But just as I was about to do that, you then said you're finished. So
well, it's obviously not finished. It's in a state of, but when you're on your own, it's very difficult to make progress, especially when it involves mathematics and major changes of concepts at the same time, because you end up getting confused all the time. And trying to use language to explain what's in my mind, hopefully will help me. And maybe at a later date I could come back and maybe give an improved presentation. I understand there's lots.
Okay, well, let's do that. That sounds very reasonable, and thank you very much for for giving us the benefit of your thinking and how it's been developing over a considerable amount of time, obviously. Now, since we have a short period of time for today, and of course we can invite you back later, I think what I might do is go very, very briefly through the questions. I've been looking at them, and actually today I think there's nothing of very great substance in the questions. Or it's mainly discussion between a lot of our regular people making interesting observations. So I don't need.
I mean, there's James Keane has put there. There's no separate week before.
I'd prefer to spend more time on James's questions and maybe one or two other people in the green room, if that's all right with you, James.
That one's just hit me. That the weak force is hidden in obscurity, but the original experimental justification for the weak force was the fact that electrons and positrons come out of the nucleus with less energy than they should do. So what appears, because if you work out the R squared energy of the R squared laws in terms of the charges, classically you should have more energy than there is observed, and this actually links with tunneling and stuff like that. But tunneling is a funny thing, because it's a theory about a theory, and you can, how can you tunnel through a theory? It just doesn't make sense. You should create a new theory, and that's all I'll say with that, because other than that, I don't understand.
Okay. Well, that's useful. Well, can we maybe just spend a minute or two maximum on the questions, and then perhaps we'll bring up James just to summarize the points he's made, and you can address those, James, if that's all right. Two Jameses. Okay. Actually, there's been some discussion about the electric universe. The contention that all these forces are ultimately electrical, and John Hodge has said, well, maybe magnetism as a fundamental allows just one force and solves all the uncomfortable problems of charge. He's just advocating that. Have you looked at all, James, at the electric universe concept of reducing, gravitation and indeed all forces of universe ultimately to electric forces? You haven't really looked at that.
I mean, the reason why I think that you need to base everything back down to a scalar theory, even if it isn't quite the same as John Hodge's scalar theory, is that people have been trying to understand gravity in terms of electromagnetism and the other way around for so long, and it doesn't work. And people are far more clever than me. But Ritz basically came up with this idea that electromagnetism should have a how do you describe it? A based ether model, and Maxwell never developed one. No one could understand the forces in a. I mean, it didn't agree with the how what's the word? Basically, the stress, strain, stability laws that you have in the terms of the all forces at a point. All forces at a point should be equal to zero and things like that. So,
okay. Well, let's if I may just be permitted to pose one or two quick questions, and then we'll go into the green room, because I think I think also Harry Ricker wants to come in as well. So, although I don't see his camera at the moment, but let's just one very, very simple thing is, where does the word toy come from? That confused me. I know a bit about the Ritzian models. Toy.
Well, the toy model is something which is partly derived, and partly heuristic. So when people say toy model, they just say, well, it sort of links ideas, but it's not wholly well argued. And so I don't claim this is a theory that's all entirely well argued, but I'm getting some links, and that's all I'm trying to stress.
I think some people might have been confused, as I was, with that terminology, but you've explained it well. The other thing is just very quickly about the speed of these forces. I mean, surely in Newtonian dynamics, the speed is taken as infinite, basically. For example, the speed of gravitational interaction.
No, it isn't taken as infinite. It's not defined. So actually, in my model, which I didn't stress, you can actually calculate the force, effectively the force on a mass, by integrating via around the actual mass. So the actual force is the gravitational field of the mass being attracted. So the gravitational field of the other mass is already there. So the integration is carried out of the mass being accelerated. So actually, you're actually taking the speed of light out of the equation. It's not that the speed is infinite. It's not that the speed is c. It's just the way if the gravitational fields are already in place, the force is only ever about the field generated by the mass plus the field that's already in place, and you calculate the force based on an integral away from the mass. So I haven't proved that, but it's in this thing. But I have calculated it.
Yeah, okay, that's interesting. But I mean, basically, in Newtonian theory, there's no aberration involved in gravitational interaction, as there is, for example, in light transmission or anything with a finite speed. But okay, perhaps we can come back to that.
But the speed does come into it. That proves why Newton is not quite right. So, but you get 99.9% of the way there by assuming the speed is not part of the solution by integrating from linearly from the around the mass that's being accelerated. If you see what I mean. I don't know whether I've got to make that more clearer.
Well, okay, that's maybe the way to derive it. But I suppose in more recent times, you have people like Van Flandern, that character, American physicist who's deceased now. But he worked out the speed of gravitational interaction from various things, looking at the difference between the maximum effect at total solar eclipse of the gravitational and the light receiving, the light being received by us and so on. He worked out that the speed of gravitational interaction was something like, I don't know, it depends. It could be 10 to the power of 20 times the speed of light. So I'm just saying that this modern conception of the speed of gravity being the speed of light is certainly quite foreign to Newtonian and also to maybe modified Newtonian analysis.
Yeah, there's some people researching MOND in galaxies where the time scales are important. So in the solar system, my contention is the time scales are not important. So Newton doesn't prove an infinite. It's just it doesn't prove any speed. It's just the speed is not part of the physical framework of the problem, because the fields are already there, and you'll just move. The masses are moving in fields that are pre-existent.
Well, if the fields are, not to label this too much, if the fields are already there, in other words, you establish a field, it's already there. That's equivalent to saying the speed is infinite, because there's no delay in.
Okay, I agree. That's semantic. I think that's semantics slightly, because that's different ways of looking at the problem. I agree. You can look at it that the speed is infinite compared to.
Okay, we just wanted your view on it, really. So, if I may now, I'm looking at the green room now because we don't have much time left, James, and I wanted to maximize this. I'm going to bring James Keane in, if I may, because he made quite a number of points. And actually, I don't think we have time to go into them in all detail. That's why I'm concerned about bringing James back, James Arathoon back. But would you like to summarize one or two of the points that you have issue with, Jim? I can't hear you. No, you're mute. Could you unmute yourself?
Have you ever heard of a game called Werewolf?
No. There, thank you. You can call me Jim to distinguish from James.
Yeah. Okay. Jim.
James, thanks for your presentation, sir. How small can R get? Apparently you don't accept that R could be zero, and therefore your quantities, both for the Coulomb's law and Newton's law of gravitation, would be infinite.
Yes, I don't.
How small can R get?
Well,
you have R in the denominator all over the place for about 1 hour. So this is a very simple question.
Quite a lot of R's. So the R's were either the radius of the universe, which is not, but the R you're specifically talking about is the radius of an electron or a proton or whatever, an elementary particle, and that
Well,
can't get to
I
zero.
said what I was referring to, James. I was referring to Coulomb's law that you presented in your slide, and also the universal law of gravitation. So I did ask, how small can the R get in those two equations?
Okay, in Coulomb's law, it can go to zero, because basically that is a law based on an interaction energy. There's two types of energies in statics, electromagnetics. In electrostatics, there's a self energy which can't go to zero, and self energy is what's dealt with in particle physics, and the interaction energy, which is an integration over the effectively R1, R2.
Excuse me, I think we're mixing up units here. I'm not talking about energy. I'm talking about force. In those equations, on the left side, we have the term F, which refers to force, which has different units than energy. So again, I asked the question, how small can R get without the force becoming infinite? If you don't have an answer to that,
as I said,
I mean, your whole presentation is down the drain. I hope you realize that.
No.
So let's get the answer.
If you look, I'll give you a reference to because I didn't.
I don't want a reference. I want what you say now. You've been thinking about this for years, and you haven't even thought about the question I'm asking.
No,
I can't believe it.
It's not a general point, Jim. I mean, these equations do blow up when R approaches zero. So it's a general question. It's not really contingent upon anything that James raised this afternoon.
Well, I'm asking when they don't blow up, how small can R get?
When there's an interaction, like in Maxwell's theory, i.e. two charges interacting, the force between two charges, the R is not a part of the radius of the particle is not considered relevant to the solution, i.e. mathematical. But when the self energy is concerned, which is not normally part of the Maxwell's theory, then that definitely blows up, and that's the problem in modern particle physics. They have to renormalize. So there's two answers to that, and I understand that my presentation wasn't very clear on that, and I wanted to put that in, but there's too much.
Well, there's a third answer too. In fact, space is quantized. That's the third answer, which you're not considering at all, apparently.
Well, no, I'm not considering that answer. So that's your theory. So I'm not saying that this is right. I'm just trying to follow the logic of my ideas as best I can, and there's flawed at the moment. I do possess, but if you look at Brillouin relativity re-examined, he does go into this issue about interaction energies and difference between interaction energies and self energies, and it's quite an illuminating discussion in his book Relativity Re-examined. Okay.
Well, I might suggest that you consider how small R can get with the force on the left side of the equation. We're not talking about interaction energies here. We're talking about force. Is a acceptable value, because without that sort of consideration, I mean, I think the whole assumption of your work is completely undermined, that space is in fact a continuous variable. Okay, that's
well, maybe, but I'm taking the assumption that space is continuous, as you pointed out, and I'm trying to run with it. So.
Okay, and I'd like to say, if I may, gentlemen, that this whole question as to whether space is continuous or discrete is another matter that we could debate at some other time. And I know you do have differing views on this. And vive la différence, that's fine with me. So I really don't think we should make this an issue of sort of make or break the theory. But thank you for raising these 2 points anyway, Jim.
Okay, thank you.
Thank you very much.
Thank you, Jim.
Okay. So it's just we have limited time, James, and I'm not blaming you for that. In fact, I'm thanking you for going on a bit longer. Some people don't even absorb the complete hour. You've given a lot of material there, and it has spawned a lot of ideas in my mind, which I haven't actually raised really because I think they would take a bit too much time. But we may in the summary, just before we let you go today, revert to some of those issues. So is there anybody else who wanted to come in? I saw Harry being popped up there for a second, but I don't know if that was accidental or not. He doesn't have any camera. Are you there, Harry? No, he's not connected. Okay, so that's fine. Now, he's come back.
I have some comments.
Yeah, so you have admin possibilities now. Go ahead, Harry. Yeah,
Hi, Harry.
we got your photo now.
Yes, good morning. James, I have a couple of comments. Okay, my comments basically have to do with, I found the presentation to be confusing in that you kind of skip from topic to topic and they don't really seem to be connected. And I think your presentation would be enhanced if you had a flow chart of how these ideas are connected. Have you thought about doing that?
Yes, I do appreciate the problem because there is a conceptual problem which I'm using a conceptual change in trying basically if you for example, if you look at the Microsoft operating system, they have a sort of HAL, hardware abstraction layer. And I think what we've done is created a sort of hardware abstraction layer in physics. And what I'm trying to get to is the underbelly of that. And I don't think that I'm quite there yet in terms of understandability. But hopefully I'm going to improve. I mean, this is partly what I'm trying to do is because I don't have any collaborators to talk with. So this is my only chance to get interaction, basically. And I apologize for the basic confused nature of the thing. It is an attempt to understand the sort of a base level physics that maybe doesn't even exist. But anyway, that's my attempt.
Yeah, and I mean, for our part, I would say that if you are able to find that your presentation today has fed back some ideas to you as to how you might progress in the future or how you might more lucidly express some of your ideas through flowcharts or something, we'd be delighted. I mean, it's a two-way process. So it's not only the information we've gleaned from your researchers, but we hope we're feeding back to a certain extent. So Harry, is there anything else that you want to raise at this stage?
I did want to mention that a lot of what he was talking about, Dirac large number hypothesis, and some of the things that he talked about do relate to the womb theory that Vladimir has been talking about. So I'd like to hear what Vladimir has to say if he's still in here.
Yeah. Okay. I was going to come to Vladimir next to see if he wanted to come in. So, Vladimir, have you any observations with regard to what you've heard today, or indeed how it might or might not relate to your own womb theory, world universe model theory?
Good morning, good afternoon, everybody. I heard this presentation. It's a good presentation, but it's far away from my ideas, from my model. There is no comparison at all. The most important, I do like theories, and they should be based on some experimental results. If you want to prove your some conclusions, some derivations, and so on and so on. Unfortunately, today there was only mathematics, there was some discussions, there was some theory without any connection to any experimental results. I'm a physicist. Physics is experimental science, and mathematics it's only serving to explain our observations. That's why it will be my proposal to the James to do something together. Experiments what we have and what they can prove in his theory. Simple like this. That's why it's. But my model is far away from what he's talking about. In my model, there are no forces. There are only energy densities, and that's it. There are only Maxwell equations. In Maxwell equations, there is no mass, there is no charge, there is nothing. There are only energy density and charge density, and that's it. It's a macroscopic values. The next very important, Jim, he asked the question about R0. What does it mean, R0? In classical physics, there is no R0. There is some minimum size, what I gave you in my presentations, and you cannot go down below this energy R. That's why there is some kind of minimum for even distance in classical physics. And the next point is very important. In my theory, gravitational constant, it depends on energy density of our medium of the world. I don't know what does it mean, ether or something like this. There are no special, even definitions what he means when he told about it. That's why so many questions I have, but not so much time we have right now to talk about it. That's it. Thank you so much for your talk. And it's very important to see something new, some new proposals, some new ideas. Maybe it will be valuable for some other ideas like myself and for somebody else too.
Yes.
Yes, that's very good that we started to talk about something new, because we should stop blaming somebody 100 years ago. We should propose something else. And it's better to put these new proposals on experimental results. This is my main point.
Well, there is a lot of scope, I think, for experimental results, because the formula beta s squared dv integral of has got this extra beta s term. Now, beta and s in the theory have the same units. So what you get left with if you take them out in dimensional analysis is integral of p dv. Now that's the core of thermodynamics. Now, if there is a field that isn't responsible for holding the particles apart, but is responsible for the medium between particles, i.e. responsible for refraction and stuff like that, then that's an interesting way to go. The other issue, which I've always thought about, is the Brownian motion, the molecular theory of gases, is fine for thermodynamics, but when you come to the theory of sound, it's very hard to because basically sound is a reversible effect. The energy is reversible. It's adiabatic from that point of view. So when sound goes through air, it isn't dispersed. If you focus it, it'll go on for as long as the wind will allow it. So people say, "Oh, well, it's been proved that Brownian motion, about the molecular theory, can prove that sound waves can go through air adiabatically without energy loss." But I'm not sure about that. So maybe we do need an extra compressibility, sort of almost like a caloric theory without being responsible for the. There's also the issue of capacitance, because I don't believe the capacitance is properly understood. So there are scopes where a huge amount of experimental knowledge is there, but it's all about interpretation, and a lot of interpretation is gone the wrong way, I think, in mainstream physics.
Okay, well, thank you very much, and thank you for raising those points, Vladimir. I think that's helped to focus our mind on the interaction between James's ideas, very seminal ideas, and our own analysis of them. I'd just like to ask: is Cornelis there? He seems to be there, and there's no camera, and there's no microphone at the moment, so I'm not sure if he's there. No, you're not there, Cornelis, are you? Because you have a few observations here which I haven't really got to. There you are. Yeah. Well, could
I'm here.
Could I just impose upon you? We've very little time left, Cornelis, but just maybe, if you'd like to give your brief reaction or criticism or approbation to what you've heard over the last hour and 20 minutes.
Well,
how does it relate to some of your own ideas?
Actually, I've been in chat a lot, but the thoughts have been rather scattered.
Right. You have various ideas about.
Delay here just a second.
Sorry, it's a bit cross-lined. No, I'm just wondering, like you have various ideas about interaction of various elements in the universe, matter and ether and tension and all that sort of thing. And do you think James's ideas and analyses are maybe complementary to that, or do you think they're completely off the wall? Or
I just think that the thoughts were far too scattered for me to really follow. I mean, it was the lecture was kind of all over the place.
There was a lot there, and maybe that's the criticism.
I'd have to go back and really listen to and several times to put it together in my head as to what was trying to be said. As far as what James said, I think James is pushing real hard for space to be quantized, and I'm not in favor of a quantized space. I'm more in favor of a continuous space, and the quantization is more of a harmonic thing. Everything is a resonant is one frequency, and then the harmonics of that frequency is the only thing that can exist. So that's why I see things as quantized, is because they have to occur in steps of that frequency.
Okay.
But,
I think one of the points earlier on, may have been raised by Quest or something, was pretty blunt to James. Oh, so do you accept an ether? So just putting that to fairly starkly, James, what is your conception of a medium of space, if indeed you have such a conception?
Well, across the various domains of physics, there has to be a space, and some of the domains claim it's a physical space. Some domains claim it's a mathematical space. But if you look about all the theories, Hilbert space, all in quantum, if you look at them all, they're all slightly different or even contradictory. And my view at the start of the lecture was we've got to create a unified view of space, and that is the prerequisite to understanding physics as a whole.
Okay.
I'm in agreement that quantum physics doesn't arise at space level once you define space. It requires it arises after that from how electrons are formed. I mean, I don't know how electron is formed. It could be a vortex. It could be a spherical body. It could be. There's various models out there, but basically, once you create that, that's the quantum. And my tendency is towards a static atom. So all the fundamental action is in the electron itself. So for example, if it's an electron that's a vortex ring, the actual frequency of the vibration is round the radius of the electron itself, rather than and that the size of electron changes depending on whether it's near a large atom, a small atom. So all the properties we're currently talking about quantum are to do with the electron properties and the other properties of the fundamental particles, and they're not space itself. They arise from space.
Right. Well, thank you, Cornelis. If I'll give you and indeed everybody else an opportunity of looking at the recording at your leisure, and if you have any further points that didn't occur to you during the presentation, we'll be happy to deal with them. So thank you, Cornelis. Actually, Jim Morrison has put maybe in words what some of the things I was trying to say. He asks it, has James even considered that the ether has variable density that is a function of the gravitational potential?
That was Newton's view, yeah.
Yes, so it's bringing in a sort of like a gravitational ether.
Yeah, but I'm not sure how to define density, because density is obviously a mass term, and I can understand that the ether can have a compressibility and a pressure, and those are required for cosmological models. But Newton and a few other people at the time talked about varying density, and Newton's model of varying density was a scalar model as well. So I have thought about it, but I can't at the moment marry up my ideas with Newton's ideas and his optics.
Okay.
Yeah.
Well, I mean, for my part, if I may sort of tend to speak not only just for myself, we'd encourage you to keep on at what you're doing. I mean, keep on looking at all these various avenues of investigation, and maybe come back to us at some stage. But time is catching up on us very, very rapidly, and I'd like to give you a few moments to say anything that you didn't say during the lecture, or indeed that arose as a result of the questions, or indeed the conversation with the people in the green room, or to summarize about what is the next phase. So I'll give you a few moments to do that, and then I'll come back and officially close the meeting. Okay, James.
Okay. Well, thank you very much for giving me the opportunity to speak, and this is part of my thinking process. And I apologize that my ideas at the moment are too confused to fit into or trying to fit as much as I've tried to in 1 hour. As I said, the basic idea is to try and get an underlying physics below the level of physics we currently have, which is based on energy and forces and such like. And in dimensional analysis terms, you can't explain a mass or a force or energy which have mass in them with another term that also has mass in it. You have to get a mass in terms of an ether or some other concept. And I've chosen ether. Einstein chose chaos space, which doesn't marry with the rest of physics, has been demonstrated for nearly 100 years or over 100 years. So yeah. So thank you very much again for giving me the chance. And as I say, I don't have a colleague to discuss these things, so I apologize that my presentation was a bit confused. Okay, thank you.
Well, our thanks are actually due to you primarily, James, because you've gone to the trouble of giving us a talk which is based on your many ideas that you've been articulating with yourself, I suppose, and questioning yourself, because you've been quite frank in saying that you don't have colleagues to discuss it with. You're not in a big team. You're not in a university. And we're delighted to have been able to keep in touch with you over the little while in my case, I've known you for just a couple of years maybe, and we've kept in touch with you. So we're delighted to have this two-way conversation, that you're able to give us the benefit of your thinking and your results and your analysis about what further needs to be done, and then maybe the input of the various people here. The eclectic influence of all the different minds that we have in the CNPS, and we all don't agree with each other, and that sometimes puts the mainstream off. They say, "Oh, look at all these cranks! They haven't even a coherent theory. They're all arguing with each other." And sometimes we get a bit heated because we feel so strongly about things. But that's the way things. It's all cut and thrust. And for my part, I'm delighted that you did. Cover so many items today. You actually covered many items, not 1, 2, 3, maybe dozens of items, which I think are they'd be very fruitful for the subject of further thought, and I'll be looking into them in more detail. And indeed, we hope to have you back again. You have in your conversations with me indicated a number of topics, and I'm personally a bit, because of my location, interested in the O'Reilly business, which Alfred O'Reilly's work over 100 years ago or less as well, that you started working on, and your research there, and you have a lot more to do, and you wanted to give a talk on this or some other item maybe, and we agreed on this. And for my part, I'm delighted that you did talk about this today, because the question of mass and charge are sort of at one point they seem to be so similar that maybe they're just different sides of the same coin. And then in another sense, in the sense that you articulated today, they're actually quite different. Their sort of similarity is really more apparent than real. So I'd like to thank you on behalf of the CNPS for taking the trouble of giving the talk today. I hope we will have you back to talk about these 1 or 2 other subjects that are already the subject of discussion between the two of us. And I'm sure all the people here will agree that we've had a very stimulating talk today. You've asked a lot of questions. You haven't given all the answers, but that's no fault at all. I think that's actually a merit, because sometimes in the mainstream, what we get is the answers. We get the high priests of the mainstream telling you, "Oh, that's all known. This is the answer. This is the answer. This is the answer." It's refreshing to have the opposite, to have all the questions posed. So on behalf of all of us here, I'd like to thank James very much for having spent the time with us today, just over 2 hours. And we look forward to having your continued participation in our work. And all of you who have participated either directly in the Green Room or through the Facebook or YouTube social media, we look forward to your further deliberations, and we'll see you next time. So I'm going to end the stream, and I'll wish you all, wherever you are in the world, a very good day.